Hello, today I'm going over atomic mass and average atomic mass lecture. So we've just been talking about the structure of the atom, history of that structure, and getting some of the basics. So these are some more of the basics in describing atoms. Okay, atomic mass is the mass of a single atom, usually measured in a very small unit because atoms are incredibly tiny. It depends on the number of protons and neutrons in the nucleus of the atom. Okay, so atomic mass depends on the protons and neutrons. So remember in our picture here, protons and neutrons are all found in the nucleus. Out here are your electrons. So for the atomic mass, I just add up the two. Number of protons, 6, number of neutrons, 6. That gives me 12. That's going to be our atomic mass. Since electrons have very little mass compared to protons and neutrons, they are usually not included in atomic mass calculations. So again, depending on how you look at electrons, they either have a negligible mass, just super tiny, or no mass at all. Each element can have atoms with slightly different masses, which leads to the idea of isotopes. So we introduced isotopes last time. We're going to go a little bit more into isotopes right now as a refresher. Actually, I guess it'll be on the next page for isotopes. An atomic mass unit, AMU, is the standard unit used to measure atomic mass. One atomic mass unit is defined as 1/12 the mass of a carbon-12 atom. This gives scientists a consistent way to compare the masses of different atoms. Because atoms are so small, using grams would result in extremely tiny and inconvenient numbers. So AMU makes measurements more practical. And you can see one AMU is basically one proton or one neutron. That's what they're getting to here. If we tried to put it in grams, once you do all these calculations, one AMU is actually equal to this number here. So this is a decimal point with 27 zeros and then 166. Very, very, very small. So it's not really practical to use that. All right, isotopes. Isotopes are atoms of the same element that have different numbers of neutrons and therefore different masses. So we're going to see this here. We're going to talk about this, but these are isotopes of carbon. So the three types of carbon I have are here, carbon 12, 13, and 14. And this is just a reminder. All carbons, all three of these different carbons have the same number of protons, 6 protons, 6 protons, 6 protons. The only thing that's changing between 12, 13, and 14 is the number of neutrons. I'm increasing the number of neutrons, okay? For example, carbon 12 and carbon 14 are both isotopes of carbon, but have different atomic masses. That's these: atomic mass 12, atomic mass 13, atomic mass 14. In nature, most elements exist in a mixture of isotopes rather than just one type. So in a sample of carbon, you're going to have a bunch of carbon 12, a bunch of carbon 13, some carbon 14, all mixed in together. This mixture is important when determining the atomic mass listed on the periodic table. Now, we haven't covered the periodic table yet, but we're getting there and we're learning some of the symbols and abbreviations that we're going to see on the periodic table. The atomic mass shown on the periodic table is actually a weighted average called the average atomic mass. This value takes into account the masses of all naturally occurring isotopes of an element and how common each element is. So that's why you see down here we have an atomic mass of 15.999 for oxygen, when really how we were talking about it, it should be a mass of 16. But this atomic mass is going to be an average of all the isotopes. And I'm going to show you on the next page, quickly at least, how that's done. More abundant isotopes contribute more to the average than rare ones. As a result, the average atomic mass is usually not a whole number. We usually will see it like this with decimals because of that averaging. So this is calculating average atomic mass. There's a lot here, but it's actually not that hard. A lot of this is going to be given to you, and we're going to have some practice with this. But this does have all the information that you need, and I'll go through this with you. To calculate average atomic mass, you multiply the mass here of each isotope by its percent abundance, written as a decimal. Here's the percent, but this would actually have to be changed to a decimal. So you'd move over, this would be, instead of 78.99%, you could write it as 0.7899. Okay. Then you add all of these values together to find the final average. So let's take a look here. I've got 3 different isotopes of, what is that, magnesium, Mg, Mg 24, 25, and 26. And then their abundance. So almost 80% of them are this Mg24. 10% are 25 and 11.01 are 26. So I've got my percentages, which you have to switch to a decimal. Then I just multiply by the mass. This will be a given, like this would, if we had a problem, this would be a given amount. So decimal multiplied by the mass will give you a number for each of these. And then we just add those all together to get the final average. And you get 24.305. You can see it should be very close to these numbers here, probably in between somewhere, right? If you got this number was 138, that would not make any sense. It needs to be close to the masses given, somewhere in the middle. Let's see here. For example, if an element has 2 isotopes, you would calculate each isotope's contribution and then sum them. This method ensures that more common isotopes have a greater effect on the final value. Like this Mg24 being 80% has the biggest effect on our final value down here. Understanding atomic mass units, and average atomic mass helps explain why elements behave the way they do. These concepts are essential in chemistry for calculations involving reactions and quantities of substances. Oh, and down here, I just have the shifting over 2 places when you have a percent to make it a decimal. So 27.5%, you shift over twice, and that will give you 0.275. So this is just a little reminder of percentages. They also help scientists identify elements and understand natural variations in matter. Overall, these ideas provide a foundation for studying atoms and the structure of matter. All right, I hope this helps. If you have questions, let me know. Thank you very much.